Okay, so one of the questions we're looking at is why 100 degrees Celsius water burns less than 100 degrees Celsius steam. And it has to do with the energy of the particles. And a good way to describe that is by looking at a heating curve, which is a graph that represents the relationship between a change in temperature as you add heat to any substance. So here we see two things happening. We see the temperature increasing, and we see the substance changing phase. So a good way to understand this is, say we have a microwave with a bowl of ice in there. For this entire period right here, the ice is getting hotter. The temperature is increasing. But when it reaches 0 degrees Celsius, it starts to melt. And as it starts to melt, during this phase right here, we see that there is literally no change in temperature. The temperature stays the same from the beginning to the very end. That's because the energy that's being added to the ice is no longer being used to increase its temperature, which is thermal energy, the energy of movement. How fast particles are moving tells you their thermal energy. But there's another kind of energy. We looked at thermal energy, we looked at phase energy, and chemical energy. Now, for a heating curve, we're not going to deal with chemical energy because there's no chemical reactions. We're only looking at, as we heat something up, does its thermal energy increase or does its phase energy increase? So in this case, if you had a bunch of solid ice particles, they're positioned like this, solid, right? Now this isn't a great drawing of what solid ice particles look like, but you can tell that they're close to each other. It looks like a solid. Now, when it goes from this point right over here to this point right over here, the energy is not going to increasing how fast those particles are moving, the thermal energy. Instead, it's going to separating those particles into a liquid. This right here is a solid, and it turns it into a liquid. That's called phase change. And the particles then are being separated from each other so that they can move around more freely. This is what a change from a solid to a liquid actually means. So the energy is no longer going into increasing how fast the particles are moving. It's thermal energy. It's going into increasing how far the particles are from each other, which is phase energy. It's a form of potential energy. Now, once the bowl of ice has completely melted, it's become a liquid. So at 0 degrees Celsius, water, if you continuously add heat to that, it's going to increase to 100 degrees, which is the temperature at which water boils. Water boils at 100 degrees, right? So at 100 degrees, the temperature stops increasing again, and it turns from liquid into a gas. Now, at this time, when it turns into a liquid to a gas, the particles again are going to be separated from their liquid phase into their gaseous phase. So in this case, from 100 degrees, and this is why 100 degree water burns less than 100 degrees steam. Because over here, it's liquid water. And over here, it's gaseous water steam, water vapor, right? So what's happening is that, again, the temperature is not increasing from here to here. It stays exactly the same. It's flat. Temperature is flat. But heat is still being added, so where is that heat going? The heat is going from turning those liquid particles into gas particles. It's separating them even further. And this actually requires a lot of energy because liquid particles are pretty close to each other. But when they're gas, they're really far away from each other, right? So these gaseous particles are now water vapor, which have a ton more energy in the form of phase energy. So again, their phase energy is increasing a ton. So what happens is that 100 degree water has way less energy than 100 degree steam. If we were to draw the energy bar graphs for that, for each of these, for ice, for liquid water, and for steam, you'd see three things here. You would see thermal, phase, chemical. The chemical energy stays the same because it's staying as water. But initially, for ice, the thermal energy is really low. And the phase energy is really low. But then, what happens is it goes from solid ice, to liquid water. Thermal energy first has to increase a little bit to the point where it can start to melt. And then as it becomes water, the phase energy increases because it's gone from solid to liquid water. But the chemical energy has stayed exactly the same, right? So then finally, it goes from water, liquid water, into gaseous steam. Now the chemical energy, once again, it's still water, so it stays the same, but the thermal energy has to increase from 0 to 100 degrees, and then the phase energy has to turn from liquid into gas. And this is where all the energy is going. It goes from first raising the temperature of ice and then changing it from ice to water. Then it raises the temperature of water and then it turns it from water into gaseous steam. So if we look back at that picture, it makes a lot of sense why the steam burn over here looks substantially worse than the 100-degree water burn, even though they're the exact same temperature.